my name is Redo Meyer. I'm the tech lead for Google's Android Developer Relations team. Every time your app initiates a data connection, no matter how much data it transfers, you cause a typical 3G wireless radio to continue drawing power for upwards of 20 seconds. This efficient data transfers DevByte will look at how you can use tools like SyncAdapters to batch and bundle your data transfers, effectively phase shifting them to produce a highly efficient, defragmented network traffic profile like this one. The underlying philosophy is to reduce the number of transfer sessions by designing for a small number of large downloads. We can do that by batching up all of our delay-tolerant transfers and bundling them together with time-sensitive ones, potentially even preempting planned future transfers. For example, if your app uses analytics rather than uploading data as it's collected, you can bundle the results together, queuing them for later upload when your app performs a time-sensitive download. Similarly, any time-sensitive transfers should also preempt updates or prefetching scheduled to occur in the near future. In each case, you're attempting to mitigate the cost of the transfer either with a delay-tolerant upload or a planned future download by having them piggyback on the time-sensitive ones. So now let's look at some techniques that you can use to implement these best practices. You can start by creating a batch queue to offset those delay-tolerant uploads. This code snippet shows a simple queue to which you can add either upload or download transfers that should occur in the future. Then, whenever you execute a time-sensitive on-demand download or the next periodic update or prefetch is initiated, you can also execute the transfers stored in your queue. This simple approach can be effective, but implemented naively, it introduces the risk of transfers being lost if your app is closed before the queue is cleared. That's fine if your queue transfers are only relevant to the current session, but for things like analytics or user-created data, you want to make sure that you never lose anything. The best solution is using a content provider. This skeleton implementation shows the basic query, insert, delete, and update methods that you would need to implement. A content provider can be backed by any data store, but most commonly an SQLite database. Now, rather than implementing a batch queue, you can insert data into your content provider, and then when your next transfer begins, query it for pending transfers and remove successfully transmitted data from that queue. In this example, I'm querying for queue check-ins, sending them to a server and removing the successfully completed ones from the queue. I still need a technique to bundle these delay-tolerant transfers with the time-sensitive ones, or possibly also reschedule those transfers periodically to ensure that they do eventually happen. Most simply, I can revisit the earlier approach of creating a series of methods to execute each transfer and then ensure that each calls the other. A much neater alternative is to use a SyncAdapter. That's going to execute each of our transfers within its onPerformSync method. It's important to note that each of the methods called should contain its own logic for determining whether or not it should actually perform an update, potentially skipping transfer sessions if the radio hasn't already been activated by a higher priority method. Using a SyncAdapter to manage your transfers has a number of advantages, including making it easy to centralize all of your app's data transfers in one place so they all run at the same time. Your data transfers can also be scheduled with transfers from other apps, all working towards the goal of reducing the number of times the system has to switch on the radio. SyncAdapter also implements data transfer best practices for you, including checking for network connectivity, retrying downloads when connectivity returns, and automated batching and time shifting on requests that occur within the same time window. Creating a SyncAdapter is actually pretty straightforward. Start by extending the abstract threaded SyncAdapter class and implementing your own data transfer code within the onPerformSync handler, as you can see here. When executing the SyncAdapter, we'll spawn a thread to invoke sync operations, so you don't need to worry about moving your code into a background thread. Similarly, multiple executions will be rejected, so you can write your transfer code knowing that it won't be run concurrently with itself. In order to run, the SyncAdapter must be bound to a service, so you also need to create a service that instantiates your SyncAdapter and binds to it. SyncAdapters were originally designed to support synchronization of a content provider associated with an account, for example, Gmail. Now, as a result, you also need to associate each SyncAdapter with an account type and a content provider authority. If you don't use accounts for your application, you can create your own mock account by extending the abstract account authenticator. In this boilerplate, you'll notice that I'm overriding the addAccount method. Here you would typically ask the user to enter their authentication details for your service, but instead you can just create a new stub account and explicitly add it to the account manager. Take particular note of the account type you specify. Like the SyncAdapter, the account authenticator also needs a service from which to run, so create a new service that binds to your implementation. Then create a metadata file for your account authenticator. Note in particular the account type, which must match the one which you provided earlier in your implementation. The sync adapter also requires a content provider. As we described earlier, a content provider is an effective and efficient way to store the data that you're planning to transfer, but if you prefer not to use one, you can create a stubbed out implementation like this. Next, create the metadata file for the sync adapter that will be used to associate a content provider and account type with it. Note that here I am marking the sync adapter as not user visible, so users won't be able to disable syncing from their global settings. Finally, add the new services and content providers to the application manifest, associating the sync adapter metadata with the sync adapter service, the account authenticator metadata with the account authenticator service. With your sync adapter complete, you can now start thinking about how to trigger your synchronizations. You can configure your sync adapter to run when server data changes, when the data on the device changes, when the framework sends a network tickle, or at predetermined intervals, or even on demand. To be as efficient as possible, it's best practice to rely primarily on server-initiated synchronizations, and where possible, avoid starting syncs as the direct result of a user action. Basically, try and eliminate the refresh button. The hardest part of the process is determining which transfers are delay tolerant and which will require a sync to be initiated. Now, this flowchart gives an indication of the most common initiators for possible syncs, and I'll go through each flow now, demonstrating how to trigger a sync adapter in each case. The best approach is to rely on server pings, notifying your app that there is new data to download. Using Google Cloud Messaging, which I'll explore in more detail in another DevByte, you can notify each installed instance of your app that it needs to sync with the server. Simply listen for an incoming GCM message notifying you of new data becoming available, and call request sync specifying the appropriate account and authority. This eliminates the need for any client-side polling while maintaining constantly up-to-date client data. Conversely, you may want to synchronize changes on the client side to the cloud. Now, this could be anything from analytics data to new email, so you want to be careful when deciding which changes are sufficient to initiate an actual transfer. If you're using content providers, you can configure your sync adapter to trigger whenever the content provider changes by setting the support's uploading attribute to true, which happens to be the default. Now, when this is set, an upload-only sync will be requested whenever your content provider executes a notify change call with the sync to network parameter set to true, as shown here. Now, within the onPerform sync handler, you can detect these upload-only syncs by examining the sync extras upload extra. This can be useful if you want to rate limit client-initiated transfers. You can also configure your sync adapter to sync whenever the platform opens a connection to keep the TCP/IP connection used for things like Google Cloud Messaging alive by setting it to sync automatically. Now, this approach ensures that your app is regularly updated without having to schedule your own client-side polling. Now, that said, the frequency of network tickles can lead to a large number of transfers, so this should only be enabled when your app is in the foreground. And even then, you may want to artificially lower the frequency of syncs within your onPerform sync method. Now, if you want to perform regular syncs at a known frequency, you can use the add periodic sync method. While you can set any frequency, this approach is more typically used to ensure at least one sync happens every 12 to 24 hours when the app isn't already running, typically with client and server changes initiating most of those updates, particularly when the app is in the foreground. Now, finally, if you need to initiate a time-sensitive transfer, either when the app launches, when the user browsers to something that you've not prefetched, or just to prefetch additional data, you can call request sync. In cases where an update must occur immediately, in order to avoid impacting the user experience, you can force a manual expedited sync by setting the manual and expedited flags within the settings bundle. These settings will ignore any backoffs and sync settings that might delay the sync and attempt to execute it immediately instead. Now, you can find all the details for creating and using sync adapters in this Android training class. So, having learned how to perform our updates efficiently, other DevBytes will look at ways to adjust our update frequency, reducing data payload sizes, and using Google Cloud Messaging in more detail.